This video will cover the Pythagorean theorem. So as a refresher, or maybe an introduction for some of you, the Pythagorean theorem states the following. A squared plus b squared equals c squared. This gives us a relationship between the sides of a right triangle. So A and B represent legs of the right triangle. These are the two sides that run perpendicular to each other. And this upside down capital T is a symbol for perpendicular. The C represents the hypotenuse, which is the longest side, and it's opposite the right angle. Now, when is the Pythagorean theorem going to come into play? Much more often than you think. But one of its primary uses that you need to be aware of is that if we have two sides, so if given two sides of a right triangle, we can always find the third side using the Pythagorean theorem. Okay, very important to know. And what we're going to do in the next part of this video is prove why the Pythagorean theorem holds true. So I have this picture set up for you where we have three squares attached to our triangle. So we have a right triangle here. Let's label the legs A, B, which would leave our hypotenuse as C. And if you look at the Pythagorean theorem, perhaps you notice, if you change your viewpoint a little bit, that it looks like the sum of area formulas for a square equals the area formula for another square, right? A squared plus B squared equals C squared. And that is why these squares are attached to this triangle, because the area of this red square should be A squared, this should be B squared, and this should be C squared. So what we're going to try to show is that the sum of the areas for the red and the green squares should be equal to the area in the blue square. So if we rearrange our picture a little bit and add in some triangles, our hope is to show that this new square that we formed on the left and this square on the right can be calculated in the same way, and then maybe we can reveal that the Pythagorean theorem holds true. So if I look at this one on the left first, this triangle, that vertical leg from before was A, this is B, B, A. So to find the area for the overall figure, each side length is A plus B. So if I multiply A plus B times A plus B, the area of the entire figure will be A plus B squared. Likewise, on the right, this is B, this is A, this length is B, and this is A. So just like the other square, its area is also calculated by A plus B squared. Now, that doesn't really do us any good because you see in these two formulas there's no c squared, so how are we supposed to prove the Pythagorean theorem? But what we're going to try to show is that if we can find an alternative way to calculate the area and show they're equivalent to what we just did, perhaps we can reveal a squared plus b squared equals c squared. So an alternative way to calculate the area would be if I take the red square, which is a squared, and I add to it the green square, which is b squared, and add to it the four triangles that are identical to each other, that will also be an alternative way to calculate the area. So the four triangles are all of the same dimension, so it would be 1/2, the base and height are A and B. If I look over at the other square on the right, an alternative way to calculate its area would be taking the area of the blue square and adding to it the four identical triangles. Now, because this is an alternative way and equally as effective as the first formula we found, we can set those two things equal to each other. because they get us in the same place. Now, this formula and this formula both equal a plus b squared. So if two things equal the same thing, those two things must be equivalent to each other as well by a property called the transitive property. So we can say the following. I'm actually going to simplify. I'm going to distribute that 4, so we get 2ab equals c squared plus 2ab. Because again, both of those formulas equal a plus b squared. And it should be evident now that if I subtract 2ab from both sides, we reveal the Pythagorean theorem and why that holds for right triangles with legs A, B, and a hypotenuse C. So let's put this thing to use. Let's do a very basic example because this example reveals one other thing that I am requiring you to do for this course. So this is going to seem pretty straightforward, but it's a good intro to simplifying radicals. So let's say we have a triangle with legs 4 and 6, and we're looking for the hypotenuse. I have two sides, so I know I can find the third using Pythagorean theorem. Just make sure you properly set up the equation. X is the hypotenuse. So x squared, 36 and 16 is 52. Take the square root. And the hypotenuse is the square root of 52. However, so that seems pretty straightforward and pretty easy for an honors level class. But the one thing I did want to introduce is how to simplify a radical for those of you who have never been introduced or have forgotten. We need to simplify the square root of 52. The first thing you want to do is check to see if it's a perfect square. 52 is not a perfect square. If this happened to be square root of 49, then we could just write x equals 7, right? So not a perfect square, so what we're going to do is break it down into its prime factorization. So all prime numbers multiplied together. So this is divisible by 2. Well, I'm going to make a little factor tree here, 2 and 26. 26 breaks down into 2 and 13. 13's prime, so I know that this is the full prime factorization. So we have 2 times 2 times 13. I'm going to group numbers in groups of 2. So I see a pairing of 2 here. For every grouping that I make, I pull that number outside of the radical once per group. So in this case, I would pull out 1, 2. Anything that I didn't group in the prime factorization goes back underneath the radical. So the simplification for the square root of 52 is 2 root 13. Another quick example, for those of you who struggled with that, let's say I had square root of 405. This is divisible by 5, so we could say 5 and 81. 81 breaks down into 3 and 27. 27 breaks down into 3 and 9. And 9 breaks down into 3 and 3. If it helps you, cross out any numbers that got broken down. The prime factorization is the following. I'm looking to group in groups of 2. So here's a group of 2. Here's a group of 2. I pull the numbers out once per group. So there's one group of 3 and another group of 3. So because I have 2 groups of 3, I should pull out a 3 twice. If multiple things are being pulled out of the radical, or if multiple numbers are being put back underneath, you multiply them together. What didn't get grouped is that 5, so it goes back underneath. And 3 times 3 is 9, square root of 5. So a quick review or quick introduction on how to simplify radicals. Prime factorization breakdown, groups of 2 for square roots, pull those numbers out once per group, multiple numbers that are being pulled out or put back underneath, you multiply together. Let's do one final example where we actually aren't given 2 sides, but we can still use Pythagorean theorem to figure out side lengths. So in this problem, there are 2 sides that are dependent on x. So I can use the Pythagorean theorem to set up an equation that will allow me to solve for x, and that's what I'm going to do. So I'm going to say x squared equals 5 squared plus x minus 1 squared. 25 plus x minus 1 squared. So remember, don't write this does not equal x squared plus 1. You don't just square each piece. Okay? We can't make that mistake at the honors level. So x minus 1 squared means x minus 1 times x minus 1. So when you FOIL that out or double distribute, whatever you want to call it, we get x squared minus 2x plus 1. Now this is an equation that I can solve for x. If you are at all fearing that you're going to have to solve a quadratic, we luck out here because the x squareds will cancel out when I move it to the other side, and we get 0 equals, I'm going to combine like terms, so 25 and 1 is 26 minus 2x. We'll get 2x equals 26, and we get x equals 13. So if x equals 13, then the side lengths for my triangle are 5, 12, and 13. So there was an example where I was able to find two missing sides, even though I was only given one. So Pythagorean theorem can come into play in certain scenarios like the one I just showed. And that is where I will conclude Pythagorean theorem. We will be using it very often this year, so make sure you understand how to set it up and when it is useful. Again, all right triangles show that relationship. So anytime we have a right triangle relationship, Pythagorean theorem could potentially come into play.